The film begins in silence. Above, the night sky shimmers thousands of stars, suspended like frozen sparks in an endless abyss. To the human eye, they appear close, scattered like diamonds on velvet, but their nearness is an illusion. Between every star stretches a gulf so vast that even light, the fastest thing in existence, requires centuries, sometimes millennia, to make the crossing. Space is not emptiness. It is separation made infinite. Yet across this silence comes a whisperin' idea, almost heretical. What if the stars are not islands adrift, but pillars of a hidden architecture? What if bridges exist, corridors of space-time folded upon itself, unseen pathways connecting suns as veins connect organs in a living body? Physicists have long spoken of such possibilities. Wormholes, Einstein-Rosen bridges, quantum tunnels, doorways, permitted not by fantasy, but by the mathematics of relativity and the mysteries of quantum mechanics. If real, they would mean that distance is not absolute, that the vastness of the cosmos is laced with shortcuts. Picture the universe not as a scatter of lights, but as a cathedral, galaxies rising like arches, stars as towering columns, and between them invisible spans of stone, bridges unseen yet essential, a structure vast, delicate, and secret. But if these bridges exist, what are they? Natural phenomena carved by gravity's relentless pull, quantum loopholes shimmering at scales too small to see, almost haunting of all deliberate constructs, signatures of intelligence unimaginably older than our own. This story is not only a scientific inquiry. It is a meditation on connection itself, on how, even across distances that should never be crossed, the universe may weave hidden threads, threads binding the stars, threads binding us. In the early decades of the 20th century, the universe changed shape not in reality, but in the human mind. For thousands of years, space had been imagined as a static backdrop, an endless stage upon which the stars and planets performed their eternal dance. But in 1915, Albert Einstein rewrote the script. His general theory of relativity declared that space was not rigid emptiness, and time was not a separate river flowing beside it. Instead, they were fused into one entity, space-time, a fabric, whose geometry could bend, twist, and ripple. This was not mere poetry. It was mathematics precise enough to describe how planets orbit, how light curves around stars, how the very universe evolves. Gravity, once seen as an invisible force pulling at matter, became something deeper, the warping of geometry itself. Yet within Einstein's equations, strange possibilities lurked. 2 decades later, in 1935, Einstein and his colleague Nathan Rosen explored the mathematics further. They discovered that under certain conditions, relativity permitted what seemed like a tunneler connection between 2 distinct regions of space-time. These passages, quickly named Einstein-Rosen bridges, were like secret corridors piercing through the geometry of the cosmos. To the public they would later be called wormholes. At first, even Einstein himself resisted the more fantastic implications. He believed these bridges were nothing more than curiosities, unstable solutions that would collapse before anything could pass through them. To him, they were mathematics, not reality, and yet the seed was planted. The suggestion that space-time might contain hidden passages could not be forgotten. By the 1950s and 60s, the physicist John Wheeler gave new life to the idea. Wheeler imagined the fabric of space-time not as a smooth sheet, but as something far stranger, a frothing, ever-changing foam at the smallest scales. In such a seething landscape, wormholes might not be rare at all. They could bubble in and out of existence constantly, appearing and vanishing faster than any particle could cross. Wheeler gave language to this vision, naming them quantum foam, and speculated about Guyon's strange entities where energy and space-time folded together at the same time. Astronomers were making discoveries that seemed to edge closer to science fiction. Neutron stars, corpses of massive stars compressed to densities beyond imagination, were confirmed. Pulsars, discovered in 1967, revealed themselves as rapidly rotating beacons, their radio pulses sweeping across Earth with clock-like precision. These objects hinted that space-time could be pushed to extremes, twisted and compacted into forms barely imaginable. Then came black holes, originally dismissed as absurd. Black holes emerged from Carl Schwarzschild's exact solution to Einstein's equations, discovered in 1916. They were regions where gravity crushed space-time so severely that nothing, not even light, could escape. For decades, black holes were considered mathematical artifacts. But by the mid-20th century, evidence mounted X-ray binaries, quasars, and finally the recognition that supermassive black holes dwell at the centers of galaxies. If space-time could curve so violently as to create these cosmic traps, could it also curve into tunnels, bridges between distant points, or perhaps even between universes? As the black hole gained scientific legitimacy, the wormhole became less of a fantasy and more of a question mark. Could such a thing exist? If so, what would it take to hold it open against the crushing weight of gravity? The rise of quantum mechanics complicated the picture further. In the quantum realm, particles tunnel through barriers they should not cross, appearing on the other side without traversing the space between. Entangled particles seemed to share states instantly, as if joined by an invisible thread outside the limits of distance. These phenomena hinted at a reality in which separation was not absolute. To many physicists, the wormhole became a symbol of these contradictions. The geometry of relativity suggested bridges, but only fleeting ones. Quantum physics suggested connections beyond space itself. Could the two be reconciled? Could wormholes dismissed by Einstein as unstable, in fact be woven into the quantum fabric? Figures such as Wheeler pressed the idea forward, blending general relativity and quantum physics in their thought experiments. Later, Kip Thorne and his colleagues in the 1980s would explore the notion of traversable wormholes in earnest, inspired partly by the imagination of science fiction writers but grounded in rigorous mathematics. They concluded that such structures could only remain open if threaded with exotic matter, a substance with negative energy density unlike anything known in ordinary physics. Exotic matter was speculative, but not impossible. The Casimir effect, observed in laboratories, showed that negative energies could indeed appear in quantum fields. Though on scales vanishingly small, parallel to theory, popular culture embraced the wormhole. From novels to television, it became the archetype of cosmic traveler door in the stars, a hidden road between worlds. While scientists debated stability and feasibility, storytellers offered visions of starships plunging through glowing tunnels, civilizations linked across the cosmos by unseen highways. Yet even beneath the fiction, the science deepened. With each decade, new discoveries pulled wormholes out of the realm of pure abstraction and into a frontier of legitimate inquiry. The recognition of black holes as astrophysical realities, the experiments confirming quantum entanglement, the early hints of space-time's foam-like structural pointed to the possibility that hidden bridges might not be fantasy after all. By The early 21st century, the conversation had matured. Wormholes were no longer dismissed outright, but studied as consequences of relativity and quantum field theory. Even if unstable, even if fleeting, they represented the profound possibility that the universe itself might be connected by unseen passages, and in 2013, the conjecture by physicists Juan Maldacena and Leonard Susskind gave the idea its most startling rebirth. R equals EPR. They proposed that Einstein-Rosen bridges and quantum entanglement might not be separate phenomena at all but two faces of the same coin. Every entangled particle, no matter how far apart, might be joined by a microscopic wormhole. The hidden bridges between stars, then, might begin not in galactic structures or cosmic tunnels, but in the quantum links between particles everywhere. It was a revelation. The universe could be laced with bridges, invisible and omnipresent. Separation might be an illusion. Connection might be the rule. But the first whispers of this story remain where it began, with Einstein, Rosen, Wheeler, and Thorne, with black holes revealed as gateways to extremes of space-time, with quantum mechanics suggesting links that defy locality, and with humanity gazing upward at the silent stars, daring to ask whether the darkness between them is truly empty, or whether, hidden in its fabric, unseen bridges already wait. The discovery phase of wormholes is not the discovery of objects, like stars or planets. It is the discovery of possibility, born in equations, nurtured in paradoxes, and now echoed in experiments. It is the recognition that the cosmos might not be defined solely by distance, but by connection, and if those bridges exist, or unstable, natural or constructed, they would mean that the universe is not the vast loneliness it appears to be, but a web in which every star is not an isolated flame, but a node in a network of unimaginable scale, a network that might already stretch between the stars, waiting for us to learn how to see it. For centuries, the night sky seemed eternal, static, and unyielding. The stars hung motionless in their places, and the void between them appeared as an unbroken silence. When Einstein's general relativity revealed that space-time itself could curve and ripple, it was a shock of beauty. But when the equations began to whisper of bridge tunnels threading unseen through the geometry of the universe, the beauty became something stranger, something unsettling. The shock came not from discovery in the sky, but from the merciless logic of mathematics. In 1935, the Einstein-Rosen bridge appeared as a consequence of general relativity. Two sheets of space-time connected at a throat, forming what would later be called a wormhole. On paper, this meant that distant regions of the universe could, in principle, be joined, a shortcut through reality itself. Yet the moment hope ignited, the equations extinguished it. Such a bridge would collapse instantly. Gravity's pull would pinch the throat shut before even a single photon could traverse it. It was an idea as cruel as it was profound. The laws of physics seemed to allow hidden corridors, but only in principle, never in practice. The universe could tease humanity with possibility while denying it passage. Later analysis confirmed this verdict. For a wormhole to remain open, it would require a substance unlike any known in nature, exotic matter, with negative energy density. This was not the matter of stars, nor the antimatter glimpsed in accelerators. Exotic matter would repel rather than attract, stretching space-time instead of crushing it. Without it, wormholes remained only mathematical phantoms. The realization unsettled the scientific world. Physics had not simply described a bridge, It had described a bridge that mocked existence. It was as though the universe contained a hidden architecture, but locked every door with an impossible key. The shock deepened with quantum mechanics. Experiments revealed that particles could tunnel through barriers, appearing on the other side without ever passing through the intervening space. Worse still was entanglement. Two particles, once linked, seemed to share a single fate, no matter how far they were separated. Measure one and the other responded instantly. Faster than light could travel between them. Einstein recoiled at this. He called it spooky action at a distance, insisting it must be an illusion. Yet by the 1960s, John Bell formulated a theorem to test it. Decades of experiments, culminating in loophole-free tests in the 21st century, proved Einstein wrong. The universe really did contain connections that defied distance. Here lay the second shock. Relativity crowned light speed as the ultimate limit, yet quantum mechanics revealed correlations that appeared instantaneous. Cause and effect, locality itself, seemed to falter. The universe was connected in ways that could not be explained by classical geometry alone. The culmination came in 2013, when Juan Maldacena and Leonard Susskind suggested a breathtaking conjecture: E equals EPR. The Einstein-Rosen bridge, and quantum entanglement EPR, might be two faces of the same reality. If true, then every entangled pair of particles was joined by a microscopic wormhole. Suddenly, wormholes were not rare monsters lurking in distant black holes. They were everywhere, in every atom, in every interaction. Hidden bridges, not between stars, but between the quantum threads of existence itself. The implications were staggering. If wormholes were the geometry of entanglement, then the fabric of the universe was a vast web of hidden connections. Locality, one of the most sacred principles of science, was no longer fundamental. Space-time itself might be woven out of entanglement, its geometry born from networks of invisible bridges, but with revelation came dread. If wormholes could connect not only regions of space, but moments of time, then causality itself was threatened. A traversable wormhole, if it could exist, would allow a traveler to depart one star and arrive at another before light itself could complete the journey. And if manipulated carefully, such a bridge could permit journeys backward in time. Here lay the true terror. If wormholes were possible, then paradox was possible. Cause could follow effect. Futures could give birth to pasts. The consistent story of reality, the arrow of time could fracture. This was not speculation from novels. It was the direct consequence of equations. Kip Thorne and his collaborators explored the mathematics in the 1980s, proving that traversable wormholes could indeed allow time travel, but only at the cost of threatening causality itself. Physics had revealed a universe in which hidden bridges might be real, but at a price so devastating that many wished them forbidden. Parallel to this, the rise of black holes deepened the disquiet. Singularities, the points at the center of black holes, represented the breakdown of space-time itself. Geometry ended there. Equations diverged into infinity. To many, this meant that general relativity was incomplete, unable to describe its own extremes. If space-time could collapse into a singularity, might it also rupture into connections? Were wormholes simply the other side of black holes, the outward bridges balancing the inward collapse? And then came Hawking's paradox. Stephen Hawking showed that black holes emit radiation, slowly evaporating over time. But if they evaporate, what becomes of the information that falls in? Does it vanish? If so, the laws of physics built on the conservation of information would unravel. Some proposed that wormholes might provide the answer. Information might escape, not into nothingness, but through hidden bridges, preserved in ways space-time itself refused to reveal. Thus, wormholes became entangled with the deepest crises of modern physics, the conflict between relativity and quantum mechanics, the paradoxes of black holes, the foundations of time itself. The shock was no longer in the possibility of bridges. The shock was in their necessity. To understand space-time, to reconcile its contradictions, wormholes or something like them had to exist in theory, if not in reality. By the 21st century, physicists looked again at the cosmos with a mixture of awe and unease. If wormholes were everywhere, they might hold the key to uniting relativity with quantum theory. If they were traversable, they might hold the key to interstellar travel. And if they could connect not only space but time, they might hold the key to unraveling causality itself. The hidden bridges between stars were no longer curiosities. They were potential cracks in the foundation of reality. And so the shock endured. The very equations that made sense of gravity and space-time also hinted at their undoing. The universe was not a fortress of order, but a cathedral with secret doors that, if opened, might lead not only across the stars, but beyond the boundaries of reason. The stars above no longer seemed silent. Between them, in the unseen, fabric, geometry itself, whispered of hidden bridge stand, of the fragility of everything humanity thought it understood. The shock of hidden bridges left science with a choice, to retreat into dismissal, or to confront the mystery head-on. The 20th century had already forced cosmology to confront the unimaginable and expanding universe, black holes as real, celestial objects, quantum mechanics with its violations of common sense, wormholes, entanglement, and exotic matter seemed as strange to be real, yet too insistent to be ignored. And so, scientists turned from speculation to investigation. The question became, if hidden bridges exist, how might they be detected? Could the cosmos itself bear their fingerprints? Light is the great informant of the universe. Every photon that reaches Earth has traced a long and perilous journey, bent by gravity, scattered by dust, stretched by expansion. Astronomers learned to use its distortions to reconstruct hidden structures. This technique, gravitational lensing, became one of the first arenas where wormholes were considered. When a massive object, such as a galaxy or cluster, lies between Earth and a distant light source, its gravity warps space-time, bending light into arcs and rings. This lensing reveals mass otherwise invisible. Theoreticians asked, what if a wormhole lay along such a line of sight? Could its geometry bend light in patterns unlike any natural object? Simulations suggested that wormholes might produce distinctive signatures, twin images, mirror distortions, or lensing without visible mass. For decades, astronomers have scoured lensing surveys, from the Sloan Digital Sky Survey to Hubble's deep fields, hunting anomalies that resist ordinary explanation. A few candidates have emerged, ambiguous and unresolved. The possibility lingers. Perhaps some arcs of light are not bent around stars or dark matter, but funneled through hidden bridges as telescopes reached their limits. Supercomputers became laboratories of the unseen. Physicists modeled space-time geometries under extreme conditions, near black holes, during cosmic inflation, at quantum scales. These simulations revealed that wormhole-like structures naturally arise in Einstein's equations, not as curiosities, but as possible outcomes of collapse, rotation, or exotic energy. Numerical relativity explored black hole mergers, searching for echoes of non-traditional geometries. If two black holes collide, might their singularities fuse into something stranger than a larger hopper, perhaps the mouth of a bridge? Some models suggested yes, though the results remained deeply uncertain. What was clear was that relativity, pushed to its extremes, created possibilities that challenged every assumption of locality. The deeper clues emerged not from the stars, but from the vacuum itself. Quantum field theory teaches that space is not empty, but seething a foam of fluctuations, particles popping in and out of existence, at extremely small scales, perhaps as tiny as the Planck length 1035 meters. Space-time itself is no longer smooth but froths like a boiling sea. John Wheeler called this quantum foam. Within it, wormholes might continually appear and vanish, ephemeral bridges flickering out before anything could traverse them. Physicists asked, could such microscopic bridges leave macroscopic consequences? Could the vast geometry of the universe be rooted in countless tiny tunnels, stitching together the very weave of space-time? The Casimir effect provided one tantalizing clue. When two plates are placed extremely close in a vacuum, they experience an attractive force, not because of matter, but because quantum fluctuations between them are suppressed. This demonstrated that negative energy densities, once deemed impossible, can exist in the laboratory. Exotic matter was no longer pure fantasy. It existed, at least in principle. The question became whether enough could exist to stabilize a wormhole. Meanwhile, quantum experiments pressed relentlessly forward. Bell's theorem had shown that entanglement could not be explained by hidden variables. Loophole-free tests proved that particles, separated by kilometers, correlated faster than light could connect them. Yet physicists resisted calling this faster-than-light communication. Information, they insisted, was not transmitted, but the correlations were undeniable, as though an invisible thread bound the particles together. The ER equals EP, our conjecture transformed this from metaphor to geometry. If entanglement corresponded to wormholes, then every entangled particle pair was joined by a microscopic bridge. Though not traversable in any classical sense, these bridges suggested a universe where separation was never complete. Every photon, every electron might carry unseen connections, threading space-time into a hidden web. The implications rippled outward. Black holes, with their entangled Hawking radiation, might be connected by wormholes to the particles escaping their grasp. The notorious information paradox, where the black holes destroyed the information they consumed, might dissolve if that information escaped through hidden bridges instead of being annihilated. Thus, investigation of entanglement was not merely philosophical, it was a pathway to solving the deepest contradictions of physics. If bridges existed at the quantum scale, then perhaps they existed everywhere, scaling upward into structures of cosmic significance. The universe itself became a laboratory. Astronomers turned to pulsars, rapidly rotating neutron stars, spinning with atomic clock precision. Their beams of radio waves, sweeping across Earth, offered cosmic metronomes. Any disruption in their timing could reveal gravitational waves, passing matter, or, just possibly, the effects of hidden geometries. Pulsar timing arrays grew into global collaborations, linking observatories across continents. In recent years, they detected subtle variations consistent with the low-frequency rumble of gravitational waves from merging supermassive black holes. Yet some anomalies persist, unexplained by conventional models. Could they be hints of space-time? structures, bridges vibrating invisibly across the cosmos. The evidence remains uncertain, but the possibility has not been dismissed. Gamma-ray bursts, two brilliant flashes from collapsing stars, were scrutinized for signatures. If photons of different energies arrived at slightly different times, it might suggest that space-time itself was not continuous, but punctuated by hidden pathways. While most results align with relativity, occasional discrepancies fuel speculation. The sky itself offers riddles, encoded in bursts of light. The most fertile ground for investigation remained black holes. Their horizons mark the boundary of knowable space-time. For decades, theorists speculated that black holes might serve as entrances to wormholes. A rotating black hole, described by the Kerr solution, contains not one but two horizons. Between them lies a region where the equations of relativity permit passage into another universe or into another region of ours. Yet these passages are unstable, collapsing under the slightest perturbation. No traveler could survive. Still, some physicists entertained the notion that quantum effects might stabilize them, or that exotic matter could prop their throats open. The Event Horizon Telescope's imaging of M87* and Sagittarius A** provided humanity's first direct glimpse of these horizons. To the public, they appeared as glowing rings. To physicists, they were windows into the very place where hidden bridges might lurk beyond theoretical constructs. Anomalies kept whispering. High-energy cosmic rays reached Earth with energies greater than expected, as though they had bypassed limitations of intergalactic propagation. Could they have traveled through shortcuts, avoiding losses expected in normal space-time? In the cosmic microwave background, the relic radiation of the Big Bang claimed to see circular patterns, faint bruises suggestive of collisions with other universes or tunnels through space-time. While most cosmologists cautioned these are statistical artifacts, the allure persists. If bridges exist, perhaps the oldest light of the cosmos already carries their marks. Gradually, a new vision emerged. The investigation was no longer only about wormholes as fantastical tunnels across stars. It was about the very nature of reality. The universe might be held together not by visible matter, but by unseen connections. Entanglement networks could underlie geometry. Negative energy densities could stabilize impossible corridors. Black holes could conceal passages to other realms. The search was ongoing, fragmentary, uncertain. No telescope had revealed a wormhole throat. No experiment had stabilized exotic matter in abundance. And yet, the pattern was unmistakable. Everywhere science probed, it found hints of connection. The deeper the investigation reached, the more the universe seemed less like a void scattered with islands, and more like a Weber hidden architecture linking stars, particles, and even universes. And with that recognition came a haunting realization. If hidden bridges exist, then humanity has already been traveling them not with ships or machines, but with every entangled photon, every cosmic particle, every whisper of information that binds the cosmos together. The investigation had not answered the question. It had only deepened it. What, truly, are these bridges? Are they pathways awaiting discovery? Are they the very foundation of space-time itself? The search pressed onward. The mystery was not receding. It was intensifying, pulling science deeper into the architecture of the unknown. The search for hidden bridges had begun with mathematics, wandered through quantum paradox, and reached into the furnaces of black holes. Yet with every step forward, the mystery grew darker. for the deeper science looked, the less stable reality appeared. If wormholes existed, if entanglement was geometry, if space-time itself was threaded by unseen corridors, then the universe was no longer an ordered map, but a labyrinth. And labyrinths conceal dangers as well as wonders. The earliest models of wormholes revealed their fatal flaw: instability. The equations of Einstein and Rosen showed that bridges pinched shut before anything could cross them. Gravity itself, relentless and unforgiving, collapsed their throats instantly. But what if, somehow, they could remain open? Later studies demonstrated that traversable wormholes demanded exotic matter substances with negative energy density. Unlike anything familiar, the Casimir effect had shown such energies exist, but only in microscopic amounts. To keep a star-sized tunnel open, one would need vast reservoirs of such exoticity. Nature, as far as observation went, gave no hint of their abundance. Yet the question of stability carried implications beyond engineering. If wormholes could form and collapse, even fleetingly, then space-time itself was unstable. It could tear, seal, and rupture in unpredictable ways. The stage of existence was not granite, but glass, fragile, fissured, uncertain. More unsettling was the paradox of causality. A traversable wormhole was not merely a shortcut in space, it was a shortcut in time. By moving one mouth of a wormhole relative to the other, a traveler could, in principle, return before departure. This was no longer speculation from fiction. Physicists like Kip Thorne and his collaborators examined the mathematics, showing that relativity permitted such loops. If they existed, wormholes could permit closed time-like curves paths through space-time that bent causality itself. What would it mean for cause and effect if an effect could precede its cause? If messages or travelers could rewrite the sequence of history? Most physicists recoiled, convinced that unknown mechanisms, what Stephen Hawking called the chronology protection, conjecture would forbid such paradoxes. Yet the mathematics resisted dismissal. The possibility remained that hidden bridges, if stable, could fracture the arrow of time. The escalation was not merely physical, but philosophical. If the universe permits pathways that collapse causality, then its coherence is not fundamental, but conditional. Reality itself could splinter under its own geometry. The mystery deepened further when cosmologists turned their gaze backward to the universe's infancy. The Big Bang was not merely an explosion of matter, but an explosion of space-time itself. For a fleeting instant, inflation drove the universe to expand faster than light, stretching quantum fluctuations into cosmic structures. In that epoch, conditions may have been ripe for wormholes. Some theorists proposed that microscopic tunnels, formed during inflation, stretching with expansion into macroscopic scales. If even a handful survived, they might still thread the cosmos. Hidden corridors born in the first fraction of a second. Cosmic inflation also raised another possibility, that the universe was not alone. In some models, inflation never ends, but continues eternally, spawning bubble universes. If so, the collisions or interactions of these bubbles might form bridges between them, gateways, not just across stars, but across entire realities. The stakes of the mystery rose from astrophysical curiosity to cosmic architecture. Wormholes were no longer only a question of whether stars might be connected, but whether universes themselves might be stitched together. The deepening enigma extended into the scaffolding of the cosmos. Astronomers mapping galaxies discovered that visible matter accounts for only a fraction of their motion. The missing Mars dark matter forms halos around galaxies, filaments between clusters, and a cosmic web spanning the observable universe. Some speculated, could dark matter be evidence of hidden bridges? Not matter at all, but the gravitational fingerprints of space-time tunnels invisible to light. If galaxies are strung along filaments, might those filaments themselves be wormhole-like conduits binding the structure of the cosmos? While mainstream science attributes the cosmic web to cold, dark matter, the speculation persists. The similarity of wormhole mathematics and cosmic filament dynamics is haunting. Perhaps the hidden scaffolding of the universe is not merely unseen particles, but unseen pathways. No mystery deepened the question more than black holes. Observations confirmed them as real. Stellar remnants collapsed into singularities, and supermassive giants anchoring galaxies. Yet at their core, the laws of physics fractured. Singularities are infinities, boundaries where geometry fails. Physicists wondered, what lies beyond the singularity? Could the collapse curve not to a point, but to another mouth? Could every black hole be, in truth, the entrance to a bridge? The mathematics of rotating black holes hinted at such possibilities. Solutions showed inner horizons, ring singularities, even potential exits, white holes, hypothetical objects where matter only escapes. Such structures, though unstable, suggested that collapse might not be an end but a passage. If true, then black holes were not graves but gateways. The galaxy's hidden bridges could be disguised as its darkest monsters. The same entities that shred stars might also conceal corridors to elsewhere. As simulations of cosmic evolution improved, they revealed another escalation. Galaxies did not float in isolation, but connected along filaments, clustering like beads on strings. Some theorists proposed that these filaments might themselves be manifestations of hidden geometry. If wormholes existed on cosmic scales, their distribution might influence galaxy formation. Some models suggested that matter could flow through such bridges, feeding galaxies from unseen reservoirs. The engines of star formation, the balance of cosmic structure, might depend not only on dark matter and gravity, but on hidden threads invisible to light. The escalation was stark. Wormholes, once considered curiosities, now hovered as potential. Architects of cosmic form at the edge of speculation. A chilling thought emerged. If hidden bridges exist, might they be traversed? Advanced civilizations, far older than humanity, might harness exotic matter, stabilize wormholes, and use them as highways between stars. If so, the galaxy could be threaded by a transportation network invisible to us, corridors of travel and communication beyond our reach. Humanity might look upon the night sky and see isolation, while in truth civilizations move unseen through hidden bridges. And yet, the Fermi paradox remained: why no evidence of such travelers? Perhaps the bridges are too unstable. Perhaps civilizations come and go too quickly. Or perhaps, more unsettlingly, the bridges are already used, but their signatures lie beyond our detection. The escalation culminated in dread. If hidden bridges exist, then space-time is not absolute. It can stretch, fold, connect, and perhaps collapse. The laws of physics that govern locality, causality, and permanence might be only provisional. In such a universe, nothing is secure. Distances are illusions, separations are masks, and stability itself is temporary. Wormholes threaten not just our models, but our sense of coherence. The universe, instead of fortress, becomes fabric, delicate, frayed, fragile. The hidden bridges between stars may not only offer hope of connection, they may also foretell collapse, instability, and the possibility that reality itself is only a temporary construction. Thus, the mystery deepened. Wormholes were not merely theoretical artifacts. They entwined with black holes, dark matter, inflation, and entanglement. Their existence, or even their possibility, threatened causality, stability, and cosmic architecture. The escalation was total. No longer confined to equations, the bridges haunted every frontier of physics. If they exist, they connect not just stars but epochs, not just galaxies but universes. If they do not, then why does every path of theory point toward them? The cosmos had revealed not clarity, but danger, an architecture of hidden threads that could link, sustain, or unravel everything. The bridges were no longer gentle speculation. They had become the dark heart of cosmology itself. The cosmos had unveiled its riddle. Bridges might exist, yet their nature remained veiled. Could they be fleeting tunnels, collapsing before a traveler enters? Could they be threads of quantum foam, shimmering at scales too small to grasp? Or might they be vast, deliberate structure signatures of intelligence hidden in the folds of space-time? Speculation is not the abandonment of science, but its frontier. And at the frontier, imagination is guided by mathematics, by experiments, by the silent whispers of data. The most grounded theory remains the one born of Einstein's equations. Wormholes are possible, but only if stabilized by exotic matter. Ordinary matter, governed by positive energy densities, cannot keep the throat of a wormhole open. Gravity would close it instantly, but exotic matter with negative energy density could act as a counterforce, prying open the passage. The Casimir effect demonstrates such negative energy in the laboratory. When two metal plates are placed extremely close together, quantum fluctuations create a pressure that can be described as negative energy between them. Tiny though this is, it proves the principle. Speculation grows. If exotic matter could be harvested or engineered in vast quantities, wormholes might not only exist, but become traversable. A stable corridor could connect stars across light years, yet no observation confirms such reservoirs exist naturally. The conventional model remains balanced between tantalizing possibility and practical impossibility. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a radical idea. Perhaps wormholes and quantum entanglement are two faces of the same phenomenon. Einstein, with Rosen, had described wormholes as bridges. Einstein, with Podolsky and Rosen, had also described entanglement EPR pairs. EPR suggested that every entangled particle is connected by a tiny wormhole. This conjecture reframed the mystery. Hidden bridges might not be rare, colossal structures, but everywhere. Every quantum entanglement, whether between photons in a laboratory or electrons across galaxies, might be a microscopic tunnel of space-atism. If it's true, the cosmos is woven into a web of invisible bridges, a universal network where separation is an illusion. Traversal may be impossible, but the existence of connection is undeniable. Entanglement itself may be the geometry of unity beyond relativity. String theory envisions the universe as vibrating strings within higher dimensional space. In some models, our universe is a three-dimensional brain floating in a higher dimensional bulk. Within this framework, wormholes could be natural conduits threading extra dimensions. Strings, stretching between brains, might serve as the skeleton of hidden bridges. Entire universes could be linked, not just stars. In this vision, a wormhole is not a tear in space-time, but a fold into dimensions we cannot perceive. Just as a two-dimensional sheet can fold into a third dimension to create a shortcut, so too could our universe fold into unseen dimensions to connect distant regions. The speculation is profound. Wormholes may not only exist within our cosmos, but between parallel branes. Each universe could be a node in a higher dimensional lattice, with bridges binding them in an unseen architecture where string theory stretches space-time into higher dimensions. Loop quantum gravity reduces it to a discrete structure. In this theory, space-time is not smooth but built from finite loop-Steiny quanta of geometry that form a spin network. In such a granular universe, wormholes could be topological features of the network. A hidden bridge might be no more exotic than a shortcut between nodes in a cosmic lattice. Stability, in this view, arises not from exotic matter, but from geometry itself. This vision makes wormholes less extraordinary and more inevitable. If space-time is woven from quanta, then hidden bridges may be natural defects, seams in the weave. Shortcuts born of structure. Speculation grows. Perhaps the universe is not vast in the way we perceive, but deeply interconnected at its base. Distance may be emergent, not fundamental. The bridges may already bind every point to every other in ways our senses cannot detect. Another speculation arises from the mathematics of black holes. If a black hole is an entrance matter falling in, light trapped, then a white hole is its mirror. Matter emerges, but nothing can enter, though no white hole has been observed. Some solutions of Einstein's equations permit them. In these models, a wormhole connects a black hole to a white hole, matter entering one universe and emerging in another. The implications are staggering. A star consumed by collapse may not vanish but may emerge elsewhere. Energy devoured in one galaxy could appear in another. White holes could be the exits of hidden bridges, their existence rewriting the narrative of destruction into one of passage. If true, the hidden bridges between stars might be the secret exchange between black holes and their unseen twins. Creation and annihilation would become reflections, the cosmos recycling itself through hidden corridors. Speculation does not end with natural processes. If wormholes can be stabilized with exotic matter, then advanced civilizations might exploit them. Carl Sagan, with physicist Kip Thorne, once envisioned such structures for interstellar travel. Wormholes, they suggested, could be engineered highways between stars. Though humanity cannot hope to manipulate exotic matter on such scales, civilizations millions of years older might. If so, hidden bridges might not only exist but be used. The galaxy could already be threaded with corridors of travel and communication invisible to human eyes. The absence of detectable travelers, the silence of the cosmos might not prove their absence. But humanity's blindness, the Fermi paradox, deepens. If advanced civilizations use hidden bridges, then our failure to see them may mean the bridges lie beyond our observational reach. Humanity could live within a galactic network without ever knowing it. Speculation extends beyond travel to destiny itself. Wormholes may not be incidental features, but fundamental architects of cosmic history. Some theories propose that wormholes could facilitate matter exchange between galaxies, feeding star formation. Others suggest they could balance entropy, transporting energy across the cosmos. On even greater scales, wormholes may shape the evolution of universes. If universes are born from black holes, as some cosmologies suggest, then wormholes could be the arteries linking cosmic generations. Our universe may be a child of another, its hidden bridges, both inheritance and legacy? If so, the geometry of wormholes is not a curiosity, but the scaffolding of reality itself. At the edge of speculation lies dread. The Higgs field, responsible for giving particles mass, may be if so, a bubble of lower energy vacuum could one day form, spreading at near light speed, rewriting physics in its path. What if wormholes could trigger such decay? A hidden bridge could connect stable and unstable regions, permitting collapse to spread. Instead of highways of travel, wormholes might be highways of destruction, unseen threats capable of unraveling existence. In this grim vision, the hidden bridges are not opportunities, but vulnerabilities. They are fissures in the architecture of reality, through which instability may one day pour. From exotic matter to entanglement, from string dimensions to quantum networks, from white holes to alien engineering, the theories multiply. Each stretches the imagination, each anchored, however tenuously, in the mathematics of modern physics. Yet no theory provides certainty. The bridges remain hidden, their signatures elusive, their existence unconfirmed. The universe gives hints: entanglement, black holes, dark matter, inflation, but never clarity. The speculation itself becomes part of the mystery. For the hidden bridges between stars are not only about astrophysical corridors, but about the limits of human understanding. They force science to the threshold of philosophy, where imagination and mathematics merge. Thus the theories converge upon a single truth. Separation may be illusion. Distance, stability, even causality may not be fundamental. Beneath the surface of stars and galaxies may lie a network of connections, a hidden architecture the universe has concealed since its birth. Whether they are quantum threads or cosmic tunnels, natural defects, or engineered constructs, the hidden bridges remain. They haunt the mathematics of relativity, the paradoxes of quantum theory, the fabric of cosmology itself. The speculation is not idle wonder. It is a mirror reflecting the fragility of knowledge, the audacity of inquiry, and the possibility that the universe is more connected than the mind can yet grasp. If the cosmos hides bridges between stars, then only the sharpest instruments can reveal them. The human eye gazes upward and sees only darkness, punctuated by scattered points of light. But modern science has built new eyes telescopes, detectors, machines that listen not only to light, but to the trembling of space-time itself. These are the tools with which humanity seeks to uncover the hidden architecture of the universe. In 2015, the Laser Interferometer Gravitational Wave Observatory LIGO detected the faintest of murmurs. Two black holes collided over 1 billion light-years away, their violent union sending ripples through space-time. Those ripples reached Earth as a tremor smaller than the width of a proton dot. Since then, LIGO, along with Virgo in Europe and Kagra in Japan, has continued to listen. Some physicists suggest that in the aftermath of such collisions, wormholes could leave echoes of reverberations distinct from those of black holes. These echoes would not be smooth fades, but faint, repeated signals, as though space-time were hollow, ringing like a drum. So far, the evidence is uncertain. A few datasets hint at anomalies, but none rise beyond doubt. Still, the instruments refine their hearing. Future generations of detectors, LISA, the Laser Interferometer Space Antenna, will orbit the Sun, listening with ears 1 million kilometers wide. Perhaps in their hum will be the signature of hidden bridges. Another tool peers directly into the abyss. The Event Horizon Telescope, a planet-wide array of radio telescopes, captured the first image of a black hole shadow in 2019. That blurred, glowing ring around darkness was proof that the geometry of space-time bends light into impossible arcs, yet theorists suggest that if a black hole were instead the mouth of a wormhole, the shadow might differ. Light could pass through, emerging elsewhere, distorting the ring into shapes unseen in ordinary black holes. The challenge is resolution. The Event Horizon Telescope pushes the limit of clarity, but even sharper instruments are needed. Future upgrades may reveal whether the abyss at a galaxy's core is not a one-way prison, but a hidden bridge. Entrance to somewhere else, to search for hidden structures, requires mapping the cosmos itself. The James Webb Space Telescope, launched in 2021, peers into the earliest light of galaxies, studying their formation. The European Space Agency's Euclid mission and NASA's upcoming Nancy Grace Roman Telescope will chart the distribution of galaxies across billions of light years, tracing the scaffolding of dark matter. If hidden bridges exist, they might subtly distort these maps. Galaxies linked by unseen corridors could cluster differently. Light traveling across a wormhole might arrive earlier, or with anomalies in spectrum. The cartographers of the cosmos search for deviations, the galaxy too bright, a cluster too distorted, a shadow cast by something not there. Each data point becomes a clue, each survey a chance to uncover the unseen .t, while telescopes look outward. Quantum laboratories look inward, into the smallest realms where hidden bridges might first arise. Experiments with entangled photons, separated by kilometers, reveal correlations faster than light could travel. Though no information passes, the link itself remains undeniable. Quantum networks extend these tests, sending entangled particles across cities, then continents. Each successful correlation proves that distance may be less absolute than once believed. Some physicists suspect that if E=EPR is true, these experiments are not only tests of entanglement, but glimpses of microscopic wormholes. One day, quantum computers and quantum communication networks may function as laboratories of space-time itself. In their data may lie the proof that hidden bridges are not myth but geometry at work. If wormholes require exotic matter, then humanity must seek it. The Large Hadron Collider, buried beneath the border of France and Switzerland, smashes particles at energies once found only in the early universe. Its greatest triumph was the discovery of the Higgs boson. But physicists also search for anomalous particles with negative energy signatures, deviations hinting at exotic matter. Future colliders, more powerful by orders of magnitude, may probe whether the Higgs field itself is stable. If unstable, the universe may one day collapse into a lower energy vacuum, a cataclysm carried perhaps along hidden bridges. These machines are humanity's attempt to tear reality open on a microscopic scale, to see whether the fabric can stretch, fold, or fracture in the depths of the galaxy. Neutron stars spin with clock-like precision, emitting beams of radiation like cosmic lighthouses. Pulsar timing arrays use these stars as a network of celestial timekeepers. Any ripple in space-time, whether from gravitational waves or from hidden structures, their rhythm already. Arrays such as Onionograv have detected hints of a background hum, a possible sea of low-frequency gravitational waves. Some suggest anomalies in timing could hint at wormholes, bridges tugging subtly on the paths of light and gravity. If confirmed, pulsar arrays may act as cosmic seismographs, mapping the hidden tremors of bridges unseen. No telescope yet sees a wormhole, no detector yet confirms a hidden bridge. But supercomputers offer another path. They simulate the equations of relativity, the dance of quantum fields, the evolution of galaxies. In their vast calculations, physicists test scenarios. A wormhole between two black holes, an entangled network at cosmic scales, exotic matter flowing through a throat. Some simulations suggest wormholes could exist, stable under certain conditions. Others show collapse inevitable. Though these are not observations, they are rehearsals. They reveal what to look for, how a wormhole might announce itself, what signature to chase among the noise of the cosmos. The coming decades bring instruments designed not only to refine, but to revolutionize. Lisa will listen for gravitational waves at lower frequencies than LIO, probing mergers of supermassive black holes where hidden bridges may lurk. The Square Kilometre Array, the largest radio telescope ever built, will map hydrogen across cosmic history, searching for anomalies of clustering and shadow. Next-generation quantum experiments will link entanglement across space, perhaps even to orbiting satellites, testing EPR beyond Earth. Each mission carries the hope of discovery, the chance to pierce the veil of distance and glimpse the hidden geometry of the universe. Yet for all the tools, the cosmos remains silent. No signal, yet shouts of wormholes. No bridge has been crossed. But science thrives not only on answers, but on the refinement of questions. With each new telescope, each new detector, humanity pushes closer to knowing whether separation is illusion, whether stars are truly islands or nodes in a vast unseen web. The search itself becomes part of the mystery. Even if hidden bridges remain unproven, the act of seeking reshapes understanding. Instruments designed to detect wormholes also illuminate black holes, dark energy, the origins of galaxies. In seeking the bridges, humanity learns the architecture of the cosmos itself, and so the tools sharpen, the testing continues, and the question endures. Not because the answer is near, but because the mystery itself propels the journey. The night sky appears eternal. To the naked eye, stars seem fixed in their positions, remote and untouchable. Yet science reveals they are not frozen, but drifting, not eternal, but mortal. Between them lies a darkness so vast that even light, the swiftest traveler known, requires centuries, even millennia, to cross the gulf. For most of history, this was the definition of isolation. Each star, a lonely island, each galaxy, a continent unreachable. And yet, whispers emerge, whispers of hidden bridges. If wormholes, entanglement, and quantum threads are real, then separation itself may be less absolute than once believed. What we call distance may be a veil-thin, fragile, deceptive. Two stars, separated by hundreds of light years, could be connected by a tunnel shorter than a heartbeat. Two particles placed across galaxies could behave as though no distance lies between them. The human imagination seizes on this idea, not merely for travel, but for meaning. To live in a universe of bridges is to live in a universe where nothing is truly alone. The longing to cross the distance between stars becomes more than ambition, it becomes the echo of nature itself. From the scale of atoms to the scale of galaxies, connection seems woven into reality. Entanglement binds particles, gravity binds stars into galaxies. Dark matter, invisible yet pervasive, binds galaxies into cosmic webs stretching across billions of light years. Perhaps wormholes, if they exist, are another expression of this law, that the universe resists isolation, that what seems scattered and broken is, at some deeper level, whole. The bridges would then not be exceptions, but continuations of a pattern written everywhere in creation. But hidden bridges also carry dread. If a tunnel exists not only across space but across time, then causality itself trembles. A traveler might arrive before departing. A message might be received before it was sent. The order of cause and effect, the spine of reality, could fracture. Philosophers have long wrestled with this possibility. If time can fold, does free will survive? If the future can influence the past, is history fixed, unchangeable already? Written, hidden bridges tempt not only with freedom of movement, but with the unraveling of meaning. Perhaps this is why nature, if it allows bridges, conceals them. To protect coherence, to preserve the illusion, or perhaps the necessity. Time's arrow, in contemplating hidden bridges, one also contemplates endings. Black holes collapse matter and time. Entropy erodes energy into silence. Galaxies drift beyond reach, carried away by acceleration. The universe itself may one day freeze, collapse, or rip apart. If bridges exist, might they endure beyond such fates? Could they link dying stars to younger ones, collapsing universes to newborns? Could the geometry of space-time weave continuity where everything else succumbs to decay? Human mortality reflects cosmic mortality. To know that the stars themselves will fade is to know that permanence is an illusion. And yet, bridges suggest continuity, that even as lights go out, connections endure. Human beings live their lives between distances, between hearts separated by misunderstandings, between cultures separated by oceans, between individuals separated by the boundaries of their own minds. The search for hidden bridges between stars mirrors a deeper longing to connect what feels separate, to overcome isolation, to find unity in vastness. It is no coincidence that wormholes and entanglement captivate the imagination. They are not just physics, they are metaphors for what humanity yearns for most. The cosmos, then, becomes a mirror. In looking outward, humanity sees its own desire for connection written in the laws of reality itself. For now, there is no confirmed wormhole, no traversable bridge. The stars remain separated by gulfs of darkness. The silence is profound, but silence is not absence. The tools sharpen, the theories deepen. The universe continues to hint through entanglement, through quantum fields, through anomalies that refuse to vanish. And so the silence becomes an invitation, an unfinished sentence, a door not yet opened, but waiting. Science is cautious, but speculation is not. Indulgence it is vision. To imagine hidden bridges is not to escape reality, but to expand it. Einstein himself began with thought experiments, beams of light, bending clocks, weaving time into geometry. Speculation about wormholes, entanglement, and hidden structures keeps alive the sense that the universe is not exhausted, not fully charted. Each possibility is a horizon, each horizon a call to continue in this. Bridges become symbols of hope, that discovery is not finished, that tomorrow's understanding may render today's impossibilities into realities. Every age of science has believed it, had reached the edge of knowledge. Every age has been wrong. The earth was once the center, then it was the sun, then the galaxy. Now, even the universe itself may not be singular, but one bubble among countless others. If hidden bridges exist, they will again overturn certainty. Distance itself, once considered absolute, may dissolve into illusion. The The cosmos would then not be a void of islands, but a web, interconnected at scales both microscopic and cosmic. The lesson is humility. Certainty is fragile. Discovery is endless. If the stars are connected by hidden bridges, then humanity is not confined but surrounded by possibilities. Each star becomes not unreachable but a neighbor. Each galaxy, not remote but part of a network. Yet the deeper meaning is not travel but belonging. To be part of a universe woven by bridges is to be part of something that resists isolation. Humanity, small and brief, is still a thread in that tapestry. The bridges remind us we are not separate, not from each other, not from the stars, not from the fabric of existence. The night sky closes in silence once more. Stars glimmer as they always have, remote, untouchable, scattered. But beneath the silence lies possibility. Beneath the distance lies connection. Perhaps wormholes lace the cosmos like unseen arteries. Perhaps entanglement binds every particle to every other. Perhaps the bridges remain hidden not because they do not exist, but because humanity is not yet ready to walk them. The universe is vast. The night is deep. The gulfs are wide. And yet, connection is the theme that will not vanish from particles to galaxies, from human hearts to cosmic webs. The hidden bridges between stars may never be seen, or one day they may carry humanity across distances once thought eternal. Either way, they remind us of something profound, that separation is never the final truth. Connection endures, and so the cosmos, vast and silent, leaves its final message not in words but in structure, not in light but in geometry, a message whispered in the fabric of space-time itself. The bridges are there, waiting.